All right, welcome. This is our second titration video. This is technically video number 8, talking about weak acid, strong base titrations, or possibly the alternate, strong acid, weak base titrations. And in the first video, we went over the basics, like what's in the flask, what species do you have to bear in mind, how does it affect the titration curve and the definition of half equivalence point. So in this video, I'm really going to be walking through some sample calculations. That's going to be the bulk of this. I'm going to be going through an example problem and showing you how you can calculate pH at 3 different points in a titration, and then but also mentioning a quick conversation about indicators and polyprotic acids. So the problem that we're going to be focusing on in this video is this one right here, 50 milliliter sample of 0.1 molar cyanic acid, Ka value is given. It's titrated with 0.1 molar sodium hydroxide, calculate the pH of the solution at 3 different points, 8 mils, 25 mils, and 50 milliliters. So we're just going to be working through these 3 parts. So part A, calculate pH with this much sodium hydroxide that has been added. The reaction that you want to write for a titration reaction is a neutralization reaction. That's going to be the first thing that you want to think about. So it's the neutralization reaction of HCN and the hydroxide, and going to Cn minus plus H2O. This is neutralization, so this is one way. And to get started, basically on any titration calculation problem, you want to start with a BCA chart. And we've done these before. We saw these before when we were looking at strong acid, strong base titrations, and it will truly work the exact same way. So I'm going to need to calculate moles of the cyanic acid and moles of the sodium hydroxide at the 8 milliliter mark. So that's what I'm going to plug in here. I'm going to plug in 0.005 moles of the cyanic acid, and at this point there is 0.0008 moles of hydroxide. Now, with strong acid, strong base, you only focus on the reactants because they were the only things that influenced pH. But now that's not the case. Now, water does not influence pH, so we can cross that column off. But the cyanide ion does, because it's the conjugate base of a weak acid. So we do need to fill in a column for that. So I know I'm starting with 0 moles because it's a product, and it doesn't say anything about starting with a certain amount of products. Those products start at 0. So just like the BCA charts from the titration problems before, you want to make your limiting reactant go to 0. So we can look at the reactants. We can tell that the hydroxide will get completely consumed. So I'm going to lose 0.0008 moles of that. So I'm also going to lose 0.0008 moles of the cyanic acid to bring it to 0.0042 moles at this point in the titration. But again, the cyanide ion does in fact influence pH, so you have to fill out a change column for that as well, because remember, this is before the equivalence point, so it's before moles of HCN are equal to moles of OH minus. You have both HA and A minus in your flask. Well, this is your A minus, right here, and so this is showing the generation of the A minus. Great, so we have filled out the BCA chart. So we've basically worked out how many moles of cyanic acid we have left and how many moles of cyanide we have generated. We want to calculate pH. Because we have both HCN and Cn minus together, we have a buffer. So the easiest way to calculate pH of a buffer is to use the Henderson-Hasselbalch equation. But to use that, we need molarity, right? We need concentrations. So we're going to recalculate concentrations of HCN and Cn minus. So the concentration of HCN is going to be 0.0042 moles over the total volume at this point, and the total volume at this point is the original 50 milliliters plus the 8 milliliters that were added. So this is 0.058 liters, and I get a cyanic acid concentration of 0.0724 molar. But then we have to do the same thing for the cyanide ion. Again, in using the Henderson-Hasselbalch, you need concentrations of both, so we're just doing the same idea. The 0.0008 moles, or 8 times 10 to the minus 4th, divided by the new added volume, gives us a cyanide concentration of 0.01379 molar. we want pH, so this is the exact same problem. I just knew I would need lots of workspace, so I'm gonna use the Henderson-Hasselbalch. Just writing the formula up here because we have everything we need. So pH is equal to the negative log of the Ka value, 6.2 times 10 to the minus 10th, plus the log of, and this is going to be the cyanide ion, and this is going to be HCN. So it's the log of 0.01379 molar divided by 0.0724 molar. And then it's all it is just plugging in and solving, because at this point it's not this is an equilibrium problem, but we can use Henderson-Hasselbalch. My smartboard is just having a moment. I'm going to let it have its moment and then continue. Great. Fantastic. So plugging in, simple, I get 9.21 for the pKa plus a negative 0.72 for that bit. So the pH at this particular point is 8.49, which addresses the question. So that's part A. Part B, calculate the pH when we have added 25 milliliters of 0.1 molar NaOH. So we've moved on, right? We're on part B now. Again, I want to start by writing the exact same reaction, that neutralization reaction, and I'm going to start with the BCA chart for the exact same reasons. I kind of want to work out what's in the flask, how much of it I have. So that neutralization reaction, HCN plus OH minus, again, this is one way, it's not in equilibrium, yields the cyanide ion plus H2O. And filling in the BCA chart. Initial moles of HCN coming from the volume and molarity, 0.005 moles, and then now we're at 25 milliliters of 0.1 molar, so this is 0.0025 moles. I don't need to fill out a column for the H2O because it does not influence pH, but I do need to fill out a column for the cyanide ion. It is a weak base, so it does influence pH. So BCA chart, make your limiting reactant go to 0. I can see that the hydroxide is the limiting reactant, so I know I'm going to wind up with 0 moles of it. So minus 0.0025. So subtract the same amount because they're in a 1-to-1 ratio. But then I also have to add 0.0025 moles to the product. Right, reactants lose, products gain. So I'm going to wind up with 0.0025 moles of cyanide and 0.0025 moles of cyanic acid. Oh, hey, look. Oh, hey, look at that. If we were to divide by the same volume, which the total volume now would be 0.075 liters, right, to calculate molarity. I know, because I have the same moles and because I have the same volume, I know that the concentration of HCN is going to be equal to the concentration of CN minus. Now, if you do not realize that, then you can use the exact same procedure that we used in the previous question and get the correct answer. And that's fine. But if you do in fact realize that your concentrations of your weak acid and your conjugate base are equal, then you can save yourself a little bit of work. Because we have equal concentrations of both HCN and CN minus, that means that we're at the half equivalence point, right? That's part of the definition of what the half equivalence point is. And at the half equivalence point, pH is equal to pKa, right? Because you have equal, this is a buffer, you have equal concentrations of both the weak acid and the conjugate base, pH is equal to pKa. So it wants the pH, great. Let's just take the negative log of the Ka value, 6.2 times 10 to the negative 10th, and save ourselves a little bit of work. The pH at this point, at this particular point, is simply 9.21. So if you do not recognize that you're at the half equivalence point, you will still get this answer if you use the right process. But if you do recognize that you're going to have equal amounts of HCN and CN minus, then you can simply make a statement that says you're at the half equivalence point, concentrations are equal, pH is equal to pKa, let's just take the negative log of the Ka value. And by the way, I did want to prove to you that the concentrations would be equal through the BCA chart, so you can make sure you have that statement that yes, indeed, I know I have the same amount of moles of each one. Okay, and then part C, calculate the pH now when we have 50 milliliters of 0.1 molar NaOH added in. Again, I'm going to start by writing the exact same reaction, that neutralization reaction, which is a one-way reaction. And I'm going to start by filling out a BCA chart for number of moles. Helpful, very helpful to see basically how many moles of which thing are in the flask. So again, this hasn't changed, the 0.005 moles of HCN, but the moles of hydroxide have changed. I have 0.005 moles of that. I know I'm starting with 0 moles of the cyanide, and I'm not including the water because that's not going to influence pH. So at this point, you should recognize this as being the equivalence point, right? You have equal amount of moles, they're stoichiometrically equivalent moles of the acid and the base. So they are both going to be completely consumed because they are using one another up. So I don't have any moles of them left over. But what I do have in my flask is the conjugate base of the weak acid. You cannot tell me that the pH here will be 7 because it will not be. You have created the weak base. You've created the conjugate base of a weak acid, and it will influence pH. It's the only thing that's in the flask, other than the sodium ion, which is neutral. So it will have an influence on pH. The pH here will not be 7. So what I've done with the BCA chart is worked out exactly how many moles of the cyanide ion we have in the flask. The cyanide ion controls pH, which means that we're going to need the cyanide ion concentration in order to do an equilibrium calculation. So I'm going to just take my moles and divide it by the total volume. So the total volume is going to be 50 plus 50. So 0.1 liters, and I get a cyanide ion concentration of 0.05 molar. So the process now going forward is basically, this has essentially changed to what is the pH of a 0.05 molar CN minus solution. Because really that's what the question now is. It's saying we have this weak base, we know that the molarity is 0.05 molar, work out its pH. So this is going back to a calculating concentration from K. But there's a bit of a problem here. This is a weak base, right? So we know we want to write, the base dissociation reaction for the weak base. We do not have a base dissociation constant. We have a Ka value. So before we go on, you need to get the correct K value that you need, and you're going to get that through Ka times Kb is equal to Kw. Kw is 1 times 10 to the minus 14th at 25 degrees Celsius. We are assuming we're at 25 degrees Celsius unless stated otherwise. This is not stating otherwise. The Ka value is 6.2 times 10 to the minus 10th. We need the Kb value because this is a weak base, so we need its Kb. So the Kb value in doing this really quick calculation, which we can do, is 1.61 times 10 to the minus 5th. So now that kind of goes along with this question. What is the pH of a 0.05 molar cyanide ion solution given that the Kb value for cyanide ion is 1.61 times 10 to the minus 5th? You should be able to solve that. That really just goes right back to stuff we were doing at the beginning of the unit. So keep in mind that at this point that question has morphed into that. What is the pH of that 0.05 molar cyanide ion solution? So now that we've moved to an equilibrium problem, this is a Kb problem. So I'm going to write a Kb reaction. Cyanide ion plus water makes HCN plus OH minus. This is not the same HCN and OH minus that got completely consumed in the titration. No. This is the HCN and OH minus that dissociates off of the cyanide ion. This is that less than 5% dissociation stuff. So this is not the same HCN anymore. And now is an ice chart. So we are using molarities now. So I'm going to use that 0.05 molar cyanide ion concentration that I worked out. I'm going to eliminate the water. I don't need that. It's not going into my Kb expression. And I'm not starting with any HCN or OH minus. Again, this is not the same HCN and OH minus that we're doing the titration with. This is the stuff that dissociates off of the cyanide ion. So I'm going to say I'm not starting with any. because the only thing in the flask at the equivalence point is this sucker. So change minus x plus x plus x, because they're all in a 1-to-1-to-1 ratio. So this is 0.05 minus x, which is approximately 0.05. I can make that assumption because KB is on the order of 10 to the minus fourth or smaller. This is x. This is x. I'm going to go to my KB expression. So this is HCN times OH minus over cyanide ion concentration, and then I'm going to start simply plugging in numbers. So my KB value, which we worked out previously, 1.61 times 10 to the minus fifth, is equal to x squared over 0.05 molar, and then you're simply solving for x. So in this case, x, which is equal to the hydroxide ion concentration, is 8.98 times 10 to the minus fourth molar. We want to get pH, so the easiest thing to do in this case is take the negative log of it, get the POH. So I'm not going to show the setup, but you take the negative log of 8.98 times 10 to the minus fourth. We get a POH of 3.05. Subtract from 14 to get the pH. pH is 10.95. Which answers the question, what is the pH at the equivalence point? But we do need to do our check. So our x value was 8.98 times 10 to the minus fourth. We assumed that when we compared it with 0.05 molar, it was going to be insignificant, or less than 5%. And when I do that math, I get that it was 1.8% associated, which is actually kind of on the high range for a weak base, showing that this is kind of a stronger weak base, but it's still under 5, so my assumption is valid. Phew, that was a lot of work. This probably involves the most amount of work calculating the pH at the equivalence point, because you've got to do that initial molarity constant calculation that we did through the BCA chart, right? Work out how many moles we have, figure out the molarity of, in this case, the conjugate base. Then you had to turn your Ka value back into a Kb value, because that's what you have at this point in the flask. You have a weak base, so you can't use that Ka value. You got to use a Kb value. And then we did the equilibrium problem, which is absolutely no different from any equilibrium problem you were doing with video number 3, but it is, you know, it's a significant amount of work. Comment about titration curves. You can see the change in the titration curve based on the strength of the acid. So this graph right here, we have strong acid on the bottom, and then the Ka values are getting smaller, right? The larger the Ka value, the stronger the acid. So the strongest acids are at the bottom and the weakest acids are at the top. Because they're all being titrated with the same base, they all end in the same point. But it's where are they starting? Right? With weaker acids, our initial pH is higher, and the pH change near the equivalence point is more subtle, meaning that steep section gets smaller and smaller and smaller and smaller. You'll notice even with this last one, right, this one that starts here and goes through here, its equivalence, its steep section is basically non-existent because the acid is so incredibly weak. So we can sort of tell from a titration curve, you know, which are the stronger acids, which are the weaker acids. Now, indicators, quick little comment about indicators. This is a chart that's from your textbook showing a whole bunch of different possible indicators and their color change and when that color change occurs. The one that we're used to seeing, phenolphthalein, is right here, and it's showing that color change from colorless over here to that really sort of fuchsia between a pH of about 8 and 9 or so. And we can pick different indicators for different titrations. The key is that you want to pick an indicator that will change color around the equivalence point pH. And as I've hopefully proven to you, not all titrations have an equivalence point pH of around 7. pH can change at the equivalence point based on what you have in the flask at the equivalence point. So you want to pick an indicator whose pKa is right around the equivalence point pH. So basically the indicator will change color when its pKa shifts ratios from having more weak acid to more weak base. So that's kind of how you want to pick out your indicator. You want to pick an indicator whose pKa kind of matches up with what you expect the equivalence point pH to be. And just to show you this, we have here, this is a weak acid strong base titration. I know that it's a weak acid strong base titration because the equivalence point pH is basic, indicating the presence of A minus, right, a weak base in the flask at the equivalence point. And we have two different indicators being shown here, phenolphthalein and methyl red. You want your indicator to actually indicate the equivalence point by changing color when you're getting right around that equivalence point pH. If you pick methyl red, you're going to basically stop your titration here, and well, that's no good. You haven't even hit your equivalence point yet, right? Your indicator changes color, but you should not be done. So picking methyl red for this particular titration is a really, really bad idea because methyl red changes in the acidic range, and we need something that's going to be in the basic range. So like methyl red is absolutely not a good indicator for this particular one. Versus phenolphthalein, which does have a color change in the basic range, so it will indicate to us that we have hit a basic pH, one that is relatively close to what the pH of our equivalence point should be. So it's a much better indicator to use. You want to pick an indicator that actually indicates around your equivalence point pH. And lastly, just a brief diagram showing you the titration curve of a polyprotic acid. Remember that polyprotic acids lose their protons one at a time. They don't lose all of their protons all at once. Even when you react them with the base, they don't lose all of their protons all at once. So what we end up having is an equivalence point for each and every dissociation. So we're starting with phosphorus acid, which I know is kind of funny because it's not pronounced phosphorus like the element, but it's phosphorus acid, and it loses its first hydrogen ion, and we wind up with H2PO3 minus. So this would be the first equivalence point. And then we have the the H2PO3 minus losing its second proton, and then we have the second equivalence point right there. So we see basically this titration curve that sort of keeps on going. And yes, I know there's a third to lose, so technically speaking, this could even sort of keep on going up here, but then notice the pHs that we're at. We would need a very, very basic, we need a very, very, very strong base to remove that final proton from that system, which, you know, you can do. You can have pHs greater than 14. 3 molar sodium hydroxide has a pH that's greater than 14. You just need basically an incredibly strong base to do that. So with polyprotic acids, you have multiple equivalence points. Your curve basically has multiple steps, each for the deprotonation of the hydrogen ions coming one at a time off of the polyprotic acid.